There are stones so small they fit neatly in the palm of your hand, but when you lift them, it can feel as though you are holding a heavy piece of human history. Welcome to Sleepy Drift into Knowing. In today's gentle science journey, we will step into the dark, quiet world of galena, a lead gray mineral that is cold, heavy, metallic, and silent, like a block of winter night drawn from deep within the earth. At first glance, galena may not shine as brightly as gold, appear as clear as quartz, or sparkle with many colors like familiar gemstones. But that quiet appearance hides a very long story. Galena is a lead sulfide mineral, the most important natural ore of lead. A small piece of galena can surprise the person holding it because it feels much heavier than it looks. It is softer than we might expect, and it breaks easily along clean crystal faces, almost like tiny cubes already arranged by the atomic order inside. But galena is not just a beautiful rock specimen in a mineral cabinet. From the earth, it has entered smelting furnaces, the history of lead and silver mining, the growth of industry, batteries, radiation shielding materials, and even some of the earliest crystal radio sets, where a small piece of dark ore could help people hear sounds carried through the air. And from that same story, galena reminds us of the other side of knowledge. Lead is useful, but lead is also toxic. Resources are valuable, but the way humans use them must come with understanding, limits, and responsibility. So in this video, we will not look at galena as a mystical stone, nor will we see it only as a dry mining resource. We will look at it as a quiet witness to the earth and to civilization. A mineral that is beautiful in its structure, heavy in its history, and profound in the lesson it leaves behind. If you enjoy slow scientific journeys, where even a small stone can open a door into the depths of the earth and the memory of humankind, you may like this video and subscribe to the channel to continue along with us. Now, before galena becomes lead in batteries, in factories, in old devices, or in the story of environmental safety, let us begin with the simplest questions. What is galena? What does it look like? And why can such a small stone feel so heavy? Let us begin with a very simple moment. A sample of galena resting on a table under a gently angled light. At first glance, it may look like a piece of silvery gray metal that has been asleep for a very long time. Its surface is not clear, not bright, and not soft-looking like jade. It has a cold, slightly dark, metallic luster, like an old mirror that reflects only a little light. But the moment you lift it, the first impression changes completely. A small stone has a surprising weight, as though inside it there is not only matter, but also the deep weight of the earth itself. The reason for that feeling lies in the chemical nature of galena. Galena is a lead sulfide mineral with the chemical formula PbS. To put it simply, each galena crystal is made mostly of two components, lead and sulfur. Lead is a very heavy element, while sulfur is an element that often takes part in many sulfide minerals deep underground. When these two elements combine in an orderly crystal structure, they create a mineral that is lead gray, metallic, opaque, and much heavier than most ordinary rocks we usually encounter. One important thing to say from the beginning is that galena is not pure metallic lead. It looks metallic because it has a metallic luster, but scientifically, it is a mineral. This is a small but very important detail. In nature, many elements rarely appear in a pure form. They usually combine with other elements to form minerals. So when we look at galena, we are not seeing pure lead lying exposed inside a rock. We are seeing a natural compound where lead has combined with sulfur and has been arranged by the earth into crystals. If we place galena beside quartz, the difference becomes very clear. Quartz usually has a much lower density, can be transparent or translucent, and when held in the hand, it gives the familiar feeling of a common silicate mineral. Calcite is similar. It is usually noticeably lighter than galena and has a distinctive reaction with dilute acid. But galena is different. Even a small piece feels solid, dense, cold, and heavy, as though its weight does not match its outer size. The specific gravity of galena is usually about 7.4 to 7.6, meaning it is more than 7 times heavier than water when compared at the same volume. This is why geology students often remember galena with their hands before they remember it from books. But galena is not remarkable only because it is heavy. It is also softer than many people expect. On the Mohs hardness scale, galena has a hardness of about 2.5. That number means it is much softer than quartz, which has a hardness of 7. It is closer to the hardness of a fingernail than to the hardness of a tough stone as we might imagine it in everyday life. So even though galena is heavy and metallic looking, it is not a strong material in the way steel is. It can be scratched relatively easily, and when handling a specimen, people need to be gentle to avoid breaking its edges or creating unnecessary dust. Here, there is a small but beautiful lesson from mineralogy. An object can be heavy, but not hard. An object can look like metal, but not be pure metal. An object can be dark in color, but have a very orderly structure inside. Galena helps us separate first impressions from scientific reality. The eyes say it looks like metal. The hands say it is very heavy. A hardness test says it is soft. And the crystal structure says it is a sulfide mineral, arranged according to clear rules. One of the easiest signs of galena to recognize is its very perfect cleavage in 3 directions at right angles to one another. Cleavage is the way a mineral tends to split along weaker planes in its crystal structure. With galena, when it breaks, it often separates into flat, bright planes that meet almost at right angles, creating the impression that this mineral naturally divides itself into small cubes. This is not because humans have cut it into box-like shapes. It happens because, inside the crystal, the atoms are arranged in an order that allows those breaking surfaces to appear naturally. That image is very important to our story. Galena is not only heavy in the physical sense, it also has a very disciplined kind of beauty. It does not bend softly like metallic lead, even though it contains lead. It is more brittle, breaks more easily, and when it breaks, it reveals fresh metallic faces that are sometimes brighter than the older, tarnished surface. Looking at a fresh, broken face of galena, we can see a cold silver light appear for a moment, as if the stone has opened a small door and allowed us to glimpse the order inside it. The color of galena is often called lead gray. That color fits its nature very well. It is not completely black, and it is not bright silver. It sits somewhere in between, muted, cold, heavy, and deep. The streak of galena, meaning the color of the mineral powder left behind when it is rubbed across an unglazed porcelain plate, is also usually lead gray. This detail helps distinguish galena from some other metallic minerals. In mineralogy, surface color can sometimes be misleading, but streak often gives a more stable clue. For example, pyrite can have a very strong metallic luster, but pyrite is usually brass yellow and much harder than galena. Graphite is also dark gray to black and leaves a dark streak, but it is much lighter than galena and has a characteristically soft, greasy feel. Hematite can have a dark metallic luster, but its streak is usually reddish-brown, like a trace of iron. Galena, by contrast, keeps its own distinct lead gray character. Cold metallic luster, heavy in the hand, soft, brittle, and with clear cubic cleavage. When these signs appear together, we no longer see it as just some general gray rock. We begin to recognize a very specific mineral identity. Imagine a small geology classroom. On the table are 3 specimens of the same size, a piece of milky white quartz, a pale piece of calcite, and a metallic gray block of galena. The first student may choose the quartz because it looks brighter, choose the calcite because its shape is easier to notice, and overlook the galena because it is dark. But as each specimen is passed from one person to another, galena immediately draws the whole class's attention. It does not need a long explanation. Its weight speaks first. Then, as the instructor turns the specimen under the light, the square cleavage faces begin to appear. At that moment, galena is no longer the dark object that was ignored. It becomes the specimen that helps everyone understand that science often begins with very simple observation. From that observation, we learn that every mineral is a collection of signs. We cannot rely on only one feature. If we look only at the gray color, we may be mistaken. If we look only at the metallic luster, we may also be mistaken. But when we combine the lead gray color, metallic shine, softness, high specific gravity, gray streak, cubic cleavage, and brittleness, the picture becomes clearer. Identifying galena is therefore like the way a scientist reads many lines of evidence at the same time, not rushing, not guessing from the first feeling. Each sign is placed beside another sign until the true nature appears. There is one more point worth noticing. Galena is an opaque mineral. Light does not pass through it the way it passes through clear quartz or through some pure samples of calcite. This fits its appearance. It does not invite us to look through it. It invites us to look at its surface, its broken faces, its shapes, and its metallic shine. The beauty of galena is not the beauty of clarity. It is the beauty of density, of weight, of a cold surface, and of a structure hidden deep within. It is like a book with a dark cover, not opened by light passing through it, but opened by patient observation. The name galena is also tied to the long history of lead ore. In many mineralogy references, galena is considered the most important ore of lead because much of the lead mined throughout history and in modern times is connected to this mineral or to ore bodies that contain it. But if we call it only lead ore, we lose part of its individual character. Before it entered a furnace, before it became metal, before it appeared in batteries or industrial materials, galena had its own geological life. It crystallized in rocks, in ore veins, in cavities, and in environments where hot water and underground chemistry worked quietly over very long periods of time. In nature, galena rarely appears as a completely lonely character. It often occurs with other minerals, such as sphalerite, pyrite, chalcopyrite, calcite, dolomite, quartz, barite, or fluorite, depending on the geological environment. Those companion minerals are like fellow travelers in the same formation story. Sphalerite tells us the ore system may be rich in zinc. Pyrite points to iron sulfide. Calcite or dolomite may remind us of carbonate rock. Quartz or barite may appear in mineral veins. When a geologist looks at galena in its host rock, they do not only ask, "What is this?" They also ask, "What kind of setting was it born in?" That question is what makes galena a doorway into the underground world. A small specimen on a table is not only an object to identify, it is a signal. It tells us that, at some point, lead and sulfur met under suitable conditions. There may have been hot fluids moving through cracks in the rock. There may have been changes in temperature, pressure, acidity, or chemical conditions that caused the mineral to precipitate. We will go deeper into those things later, but even now, the mere presence of galena shows us that rocks are not completely lifeless things. Rocks preserve processes, and minerals are small letters in that language. This also helps us understand why galena has two sides in the human story. On one side, it is beautiful in a quiet way. Heavy, metallic, clearly geometric, easy to identify, and very worthy of a place in the specimen case of a museum or classroom. On the other side, because it is a lead-bearing mineral, it reminds us that natural beauty does not mean absolute harmlessness. A solid galena specimen, stored and handled properly, can be observed and studied safely. But it should not be ground into powder. It should not be handled casually by children as a toy. It should not be brought near food, and you should wash your hands after touching a specimen. This is not fear. This is the calm attitude of science. In that very attitude, galena becomes even more memorable. Science does not require us to avoid everything that carries risk. Science teaches us to understand where the risk is, under what conditions it appears, and how it should be handled. The lead in galena is the reason it is heavy, the reason it matters in the history of metallurgy, but also the reason modern humans must be careful with lead dust, lead exposure, and environmental pollution. From the very first stage of identification, galena shows us the larger message of this entire journey. Natural resources are not only meant to be extracted, but also to be understood correctly. If we place galena under a magnifying glass, its surface is no longer just a dark gray area. We may see tiny edges, reflecting faces, broken marks, and sometimes square crystals or nearly cubic blocks. A perfect museum specimen may be much brighter and sharper than many field samples. A specimen from a mine may be mixed with host rock, covered by other minerals, or appear only as metallic gray specks within a larger rock mass. This reminds us that the most beautiful images in books and on screens are often carefully selected. In real life, geologists must learn to recognize galena even when it does not appear in an ideal form. That is also a useful lesson for the viewer. Not every truth in nature appears in a perfect shape. Crystals can be distorted, broken faces can be dull, specimens can contain impurities, and light can change the way color appears. But the true nature can still be recognized by combining many signs. And when we learn to look this way, we are not only learning about galena. We are learning a slower way of seeing the world, not rushing to be charmed by appearances, and not rushing to ignore a dark object just because it is not brilliant. We could say that galena is a mineral of contrasts. It is soft but heavy. It is brittle but neatly geometric. It is dark but metallic. It lies still in rock, yet it has entered very active currents of history. It can be beautiful in a display case and useful in industry, but it also demands caution because of lead. All of these contrasts do not make the story more confusing. Instead, they make galena a deeper subject. Because in nature, the things most worth learning about usually do not have only one side. Now that we know galena is a lead sulfide mineral, with a lead gray color, metallic luster, softness, brittleness, very high weight, gray streak, and clear cubic cleavage, that dark stone is no longer nameless. We have begun to see it as an orderly structure, a geological sign, a source of metal, and a reminder of responsibility. But the next question goes even deeper. How did the Earth create a mineral like this? Galena does not simply appear from nothing. It needs lead, it needs sulfur, it needs the right chemical environment, it needs hot fluids moving through rock. and it needs enough time for the darkness underground to turn separate elements into a crystal mass as heavy as a winter night. For a galena crystal to be born, the Earth needs more than just a bit of lead sitting somewhere inside rock. It needs a pathway for lead to move, sulfur for it to combine with, hot water or underground brine to act as a carrier, cracks or open spaces where the mineral can precipitate, and chemical changes subtle enough to make atoms drifting through a solution stop, attach to one another, and become part of the rock. In other words, galena is not an accident. It is the result of a slow meeting between metal, sulfur, water, rock, and time. In many ore deposits, galena forms from hydrothermal fluids. The word hydrothermal may sound complicated, but it can be understood simply as hot fluids moving underground. They are not like rivers on the surface. They have no light, no obvious sound of flowing water, and they often move through rock by way of tiny cracks, small pores, or rock layers that allow water to pass through. These fluids can carry many metal ions, including lead. When they enter the right environment, lead can combine with sulfur and then precipitate into the lead sulfide mineral we call galena. This helps us see galena in a broader way. A galena specimen on a table is not just a heavy gray block. It is the trace of an ancient fluid that once moved through rock. That fluid may have been hot, salty water in a sedimentary basin. It may have moved through carbonate rocks such as limestone or dolomite. It may have slipped into fractures, fault zones, and small cavities, then left galena behind like a chemical deposit in the dark. When we hold that specimen, we are holding part of the result of quiet movement beneath the ground. The lead in galena may have been taken from nearby rocks or from deeper rock layers. Under certain conditions, hot and salty groundwater can dissolve small amounts of metal from rock. It does not dissolve metal in a fast, obvious way, like sugar dissolving in tea. This process is usually slow, depending on temperature, salinity, the chemical makeup of the fluid, acidity, and many other factors. But over geological time, even very small amounts being carried again and again can build up into a significant ore body. This is one of the important lessons of geology. Very slow processes can still create very large results as long as there is enough time. Sulfur is the other half of the story. If there is lead but no suitable source of sulfur, galena will not form according to its true nature. Sulfur in an ore system can come from many different sources, depending on the geological environment. In some cases, it is related to sulfate in ancient seawater or in sedimentary rock, later transformed into a form of sulfur that can react with metal. In other cases, it may be connected to deeper processes in the Earth's crust. The important point is that lead and sulfur must meet under chemical conditions that allow lead sulfide to become insoluble and begin to precipitate. That precipitation can happen when hot fluid cools, when it mixes with another fluid, when acidity changes, when oxidation-reduction conditions change, or when it meets rock that can react with the fluid's components. Oxidation-reduction conditions can be understood simply as how much an environment tends to accept or give up electrons during chemical reactions. This is an important idea in geochemistry because many metals can either dissolve or precipitate depending on those conditions. So galena is not just the product of hot water with lead in it. It is the product of a very specific chemical system. In ore veins, galena can fill cracks the way mineral material fills a fracture in rock. At first, there is only a small open space. Then fluid passes through and leaves a layer of mineral on the wall of the crack. Later, another pulse of fluid arrives, bringing more metal and sulfur, and precipitation continues. Across many stages, a fracture can become filled with galena, sphalerite, calcite, quartz, barite, or other minerals. If there is enough open space, galena crystals may grow into clearer cubic forms. If the space is too tight, galena may crystallize as a dense mass with less beautiful shape, while still keeping its chemical nature. In carbonate rock, the story has another layer. Carbonate rocks, such as limestone and dolomite, can react with ore fluids. Instead of simply filling empty spaces, new minerals can replace part of the older rock. We can imagine this process as part of the original material being dissolved or changed, while galena and related minerals take its place. In many Mississippi Valley-type lead-zinc deposits, ore bodies are often found in carbonate rock, and the main minerals may include galena and sphalerite. Deposits like these show that ore does not always have to be directly connected to an erupting volcano. Sometimes, the origin of an ore deposit lies in hot brines moving through vast sedimentary basins, much quieter than the image of glowing red lava. This is a point that is very easy to misunderstand. When people hear that minerals form underground, many immediately picture molten magma cooling down. That is true for some minerals and some types of rock, but it is not the only way minerals are born. Galena is often better explained through the story of hydrothermal fluids and chemical reactions inside rock. It does not need to crystallize directly from a sea of magma. It can form when hot fluids carrying metals move through tiny pathways in the Earth's crust, then leave lead sulfide behind when conditions change. The quietness of that process fits galena's appearance very well. Not explosive, not blazing, but persistent and deep. Galena often occurs with sphalerite, a zinc sulfide mineral. This partnership is not random. Lead and zinc can be carried by the same ore-forming fluid system, then precipitate near each other when conditions are right. In an ore sample, galena may appear as metallic gray areas, while sphalerite may be brown, black, honey yellow, or reddish-brown, depending on its composition. These two minerals are like two signs from the same geological story. A fluid system was once rich enough in metals to create lead-zinc ore. When geologists see them side by side, they do not see only two minerals. They see a system. Pyrite can also appear in the same environment, but pyrite is an iron sulfide, not a lead ore. It has a brass yellow color and is usually much harder than galena. Chalcopyrite, a copper-iron sulfide mineral, may also appear in some polymetallic ore systems. Calcite, dolomite, quartz, and barite tell other parts of the story. Calcite and dolomite point toward carbonate rock or carbonate-rich fluids. Quartz can fill veins in many hydrothermal environments. Barite, a barium sulfate mineral, may show that the fluid once contained barium and sulfate. Each companion mineral is like a small witness, helping us understand the conditions of the fluid that once passed through. A galena ore body is not necessarily created in one single event. Many deposits have a history of mineralization in several stages. Some minerals arrive earlier, and others arrive later. A fracture may open, become filled, and then crack again. Older crystals may become surrounded by a new layer of mineral. Sometimes galena crystallizes together with sphalerite. At other times, calcite or barite arrives later and covers the remaining open spaces. Because of this, a small slice of rock can look like a layered diary. Someone who knows how to read it can see the order of events, almost like reading tree rings to understand the life of a tree. The size and shape of galena crystals depend greatly on the space where they grow. In a cavity with enough room, crystal faces can develop more freely, creating sharp-edged cubes. In a narrow ore vein, galena may be forced to grow alongside other minerals, forming denser masses with fewer complete shapes. This also explains why museum specimens often look much more beautiful than ordinary mined ore. Museums usually choose samples with clear crystals, while in a mine, most minerals exist in a more practical way, mixed with rock, inside veins, inside ore bodies, and not always showing perfect geometric beauty. But whether the crystal is beautiful or not, its origin is still a story of conditions. Not every place with a little lead becomes a galena deposit. There must be a metal source, a sulfur source, a transporting fluid, pathways through rock, and chemical or structural traps that allow ore to accumulate. If one of these conditions is missing, lead may remain too widely scattered and never form an ore body. So a galena deposit is the result of many factors meeting at the right time, in the right place, for long enough. It is a rare concentration of matter, not something obvious or guaranteed. Geologists cannot travel back in time to directly watch those ancient hot fluids move. They must infer the story from the evidence left behind. They observe the relationship between galena and the surrounding rock. They look at which mineral cuts across which other mineral to understand what formed first and what formed later. They study fluid inclusions, tiny droplets of fluid trapped inside crystals as the minerals grew. They analyze lead isotopes or sulfur isotopes to look for clues about the source of the material. They measure the chemical composition of companion minerals. Each measurement does not tell the whole story by itself, but when placed together, they help reconstruct a geological history with a real foundation. Lead isotopes are especially interesting in the story of galena. Lead has several different stable isotopes, and the ratios between those isotopes can carry information about the source of the lead or the geological history of the ore system. To put it in a more familiar way, isotopes are like slightly different versions of the same element. They have the same basic chemical behavior, but different nuclear masses. When scientists measure isotope ratios in galena, they can compare them with different rock sources to understand where the lead may have come from. This does not always give a simple answer, but it turns galena into a storage place for information, not just an ore to be melted down. Similarly, the sulfur in galena can also carry traces of its origin. Sulfur isotope ratios can help suggest whether the sulfur came from sedimentary sulfate, biological processes, deeper sources, or a mixture of several sources. In real ore systems, the answer is often complex. A single deposit may have several stages of fluid movement, multiple sources of material, and many episodes of change. So when we talk about the origin of galena, we should keep a sense of scientific humility. There are strong models and good evidence, but each specific deposit still needs to be studied through its own data. Near the surface of the Earth, galena may no longer be as stable as it was in the deeper environment where it formed. When exposed to water, oxygen, and weathering conditions, galena can transform into secondary lead minerals, such as cerussite, anglesite, or pyromorphite, depending on the chemical environment. This is why the upper zones of some lead deposits may contain many lead minerals other than galena. That transformation reminds us that minerals do not stand outside of time. A mineral can be born in deep darkness, and then, when rock is lifted up, eroded, and brought close to the surface, it enters a new chemical chapter. The formation story of galena, therefore, does not end with a formula. The formula tells us it is lead sulfide. But geology tells us why lead and sulfur met, where they met, by what pathway, in what kind of rock, under what conditions, and what traces they left behind. A formula is like the title of a piece of music. The formation history is like the way that music is played in a dark room through many slow rhythms, many layers of sound, and many pauses. Galena only seems silent when we do not yet know how to read it. Once we understand more, we can see that inside that silence is the very long movement of the Earth's crust. We can imagine a scene from millions of years ago. Deep underground, inside a layer of carbonate rock, hot brine is slipping through tiny cracks. It is not bright, not loud, and not dramatic like an eruption. But inside it are metal ions being carried through the darkness. When the water reaches a zone of rock with the right chemical conditions, lead begins to meet sulfur. The first particles of lead sulfide attach to the walls of the fracture. Then another layer forms, then another. Time moves so slowly that no living creature could watch it happen with the naked eye. But eventually, a galena vein forms, heavy, gray, and metallic, like a chemical river turned to stone. That scene helps us understand Galena much more deeply. It is not only a source of lead that humans would later extract, it is evidence that underground systems can transport matter in subtle and complex ways. It shows that rock is not always motionless in an absolute sense. Across a human lifetime, rock may seem still. But across geological time, the Earth's crust can crack, water can pass through, metals can move, minerals can precipitate, ore deposits can be born, and later those deposits can be lifted, eroded, exposed, and finally found by humans. When humans mine Galena, they usually see only the final part of that geological story. An ore body is drilled, dug out, crushed, processed, and then sent into metallurgy. But before machines and factories existed, there was a natural process far longer than anything humans built. Lead was transported through rock. Sulfur was present at the right moment. Fluid conditions changed in the right place. Minerals filled fractures or replaced carbonate rock. So every 2,205 pounds of ore, or about 1 metric ton, is not only a resource, it is the result of a complex geological arrangement that humans need to understand and respect. Here, the two-sided message of Galena becomes clearer. The underground world created a mineral that is heavy, beautiful, and useful. Humans learned how to extract lead from it, use lead in many technologies, and sometimes find silver associated with the ore. But the more we understand Galena's formation process and composition, the more we see that mining cannot be only about taking. It needs geology to find the right place. It needs chemistry to process the material correctly. It needs environmental science to control waste. It needs medicine and toxicology to understand the risks of lead. A small piece of Galena therefore connects the underground world with the full responsibility of human life on the surface. And when we place the Galena specimen back under the light, its gray color seems a little deeper. Before, we knew it was heavy because of lead. Now, we know it is also heavy because of an entire history of formation inside the Earth's crust. It was once a chemical reaction unfolding in darkness. It was once a precipitate on the wall of a fracture. It was once part of an ore body, then became a specimen, a mined resource, an industrial material, and a reminder that natural matter always has a story longer than its appearance. From that origin, we can move even closer into the Galena crystal itself, because inside that seemingly simple gray color is an orderly atomic structure, where lead and sulfur are arranged in a way that creates weight, metallic shine, cleavage, and even a property that once helped humans hear radio signals from the air. From its origin underground, let us move even closer, close enough that we no longer see Galena only as a heavy gray stone, but as a very orderly arrangement of atoms. If we could shrink our bodies down to a size smaller than a speck of dust, then step inside a Galena crystal, we would not see a chaotic pile of matter. We would see lead and sulfur repeating in a regular crystal lattice, like an invisible city built from extremely precise positions. That repetition is what creates the cubic shape, the flat cleavage surfaces, the cold metallic luster, and the dense, heavy feeling we noticed when holding the specimen in our hand. The crystal structure of Galena belongs to the cubic system. In simple terms, this means the units inside the crystal are arranged in balanced directions, creating a tendency to form square or nearly square blocks. Many mineralogy books often describe the structure of lead sulfide in Galena as similar to rock salt, meaning a type of arrangement in which ions are placed alternately in a regular lattice. We do not need to imagine this as a stiff brick wall. Instead, we can picture it as a geometric piece of music, where each atom has its own position, and the entire crystal keeps repeating its rhythm through space. Because of that crystal lattice, Galena has very clear cubic cleavage. When a crystal is affected by force, it does not break completely at random like an ordinary piece of glass. It tends to split along weaker planes in its structure, creating flat surfaces that meet almost at right angles. Someone who has not studied mineralogy might think the Galena block was already cut by human hands. But in reality, the inner order itself guides the break. This is one of the most beautiful moments in materials science. The outer shape is not decoration, but a trace of the invisible structure inside. When we look at a Galena crystal under angled light, we can see its flat faces reflect light in a very distinct way. Its metallic luster does not come from being pure metal, but from the way its surface and the electrons in the material interact with light. Galena is a sulfide mineral with a metallic appearance. It is opaque, and it does not let light pass through the way clear quartz does. It does not glow brightly, and it does not sparkle in many colors. It reflects light with a quiet, cold look, like a dark mirror that has been buried in stone for a very long time. That gives Galena a kind of beauty that is not loud, but very memorable. Galena's weight also begins from within. The element lead has a large atomic mass, so when lead makes up an important part of the mineral structure, the entire crystal becomes very heavy for its volume. This is why a small Galena specimen can surprise the palm of your hand. It reminds us that weight does not depend only on size. Two objects with the same shape and volume can feel very different if their atomic makeup is different. A piece of quartz and a piece of Galena of the same size do not tell the same story. Quartz tells the story of silicon and oxygen in a silicate lattice. Galena tells the story of lead and sulfur in a much heavier sulfide mineral. But the interesting thing is that Galena is both heavy and soft. In everyday thinking, many people assume that a heavy object must also be very hard. Galena helps correct that instinct. Hardness is the ability to resist scratching, while density is the amount of mass in a given volume. These two properties do not necessarily go together. Galena has a high density because it contains lead, but its hardness is low compared with many familiar minerals, so it can feel solid and heavy in the hand, while still being easy to scratch, easy to chip along the edges, and brittle under pressure. Once again, This stone teaches us not to judge matter through only one sensation. The brittleness of galena also has its own meaning. Metallic lead can be soft and easy to bend, but galena does not behave like metallic lead. In galena, lead has combined with sulfur in a crystal lattice. Because of that, it cannot be bent into wire or sheet the way pure lead can. When enough force is applied, it tends to break rather than deform in a flexible way. This difference is very important. It shows that when an element becomes part of a natural compound, it can have properties very different from its pure form. The lead in galena is no longer a soft lump of metal sitting freely. It is part of a mineral structure. From that structure, we can move to a detail that makes galena special in the history of technology. Galena is a natural semiconductor. A semiconductor can be understood simply as a material that does not conduct electricity as strongly as a metal, but also does not completely block electricity the way many non-metallic materials do. It sits somewhere in between, and under certain conditions, electric current can pass through it in a very useful way. Today, when we hear the word semiconductor, we often think of silicon in modern integrated circuits. But long before the age of integrated circuits, a small piece of natural galena once helped humans rectify signals in crystal radios. To understand that story, let us imagine a quiet room in the early 20th century. On the table, there is no screen, no complicated amplifier, and no powerful battery like the ones in modern electronic devices. There is only a coil of wire, a simple capacitor, a sensitive earphone, a thin metal wire, and a piece of galena. That wire was often known by a very visual name, a cat whisker. It was touched gently against the crystal surface to find an active point. When the contact was right, the meeting point between the metal and the crystal could allow the very weak alternating electrical signal from radio waves to be rectified, meaning changed in a direction that allowed the earphone to reproduce sound. This point needs to be stated carefully. A piece of galena does not produce sound by itself. It has no mysterious power. It only takes part in a very simple electrical circuit, where an antenna receives radio waves, the coil and capacitor select the signal, and the contact between the cat whisker and the galena helps rectify that signal. But that very simplicity makes the story beautiful. A mineral born underground, once the result of hot fluids and chemical reactions deep inside rock, could later sit on the table of a radio listener and help turn electromagnetic vibrations in the air into a small voice in an earphone. Not every point on the surface of galena worked equally well. In old crystal radios, users often had to search by gently moving the tip of the metal wire across the crystal surface until the sound became clearer. A very small change in position, pressure, or contact shape could weaken the signal or make it disappear. This shows that a galena detector was both clever and fragile. It made use of natural semiconducting properties, but it was not as stable or easy to use as the semiconductor diode developed later. That is why users at the time had to be patient, almost as if they were listening to the stone through their fingertips. From a modern point of view, we could call that contact a very early form of metal semiconductor contact. It could work like a rectifier, allowing current to pass more easily in one direction than in the other. But in the story of everyday life, it does not need grand words to become memorable. Imagine a person quietly wearing earphones, turning a tuning knob, touching a thin wire to the lead-gray crystal, and then suddenly hearing a voice from far away. In that moment, galena was no longer only an ore in a mine. It became a small bridge between the underground world and the radio sky. This story does not make galena the direct ancestor of all modern technology in an overly simplified way. Materials science and electronics developed through many steps, with many different materials, theories, and devices. But Galena holds a special place in history because it shows that humans had learned to use the electrical properties of natural crystals before fully understanding the semiconductor world as we know it today. It was like a door that opened early. Through that door, humans began to realize that inside solid objects that seemed silent, there could be very subtle electrical behavior. Today, lead sulfide is still a material of interest in materials science, especially in devices related to the infrared range and in nanocrystal research. However, we need to clearly distinguish between natural galena in a mineral specimen and lead sulfide that is manufactured, refined, and controlled in a laboratory. A piece of galena in a collection cabinet is not the same as a modern sensor produced with controlled purity, size, film layers, and electrical structure. They are both lead sulfide, but the context of use is different, the level of control is different, and the safety requirements are also different. This is how science helps us avoid confusing an interesting fact with exaggeration. From here, we can see Galena as a meeting point between three worlds. The first world is mineralogy, where Galena is identified by its lead gray color, metallic luster, low hardness, high density, and cubic cleavage. The second world is geology, where Galena is born from hydrothermal fluids, fractures, carbonate rock, and the chemical history of the underground. The third world is materials physics, where that same mineral shows semiconducting behavior, responds to metal contact, and once played a role in crystal radios. A small stone suddenly becomes the intersection of chemistry, geology, physics, and the history of technology. That intersection is what makes Galena different from an object described only by its use. If we only say Galena is lead ore, we see it only as raw material. If we only say it has cubic crystals, we see it only as a specimen. If we only say it was once used in radios, we see it only as an old technical detail. But when we place all of these things together, Galena appears as one continuous story. Born underground, heavy because of lead, shaped by its structure, reflecting light through its surface, carrying special electrical properties, and then discovered and used by humans. This is the beauty of knowledge. Each small fact does not stand alone, but connects to a larger network. We should also remember that Galena's semiconducting property does not remove the lesson of caution about lead. An object can be important in technology and still need to be handled safely. In old crystal radios, the Galena piece was usually a small part of the device, not something to grind, burn, lick, or touch carelessly. Today, when collecting Galena, people should still keep the specimen in a box, avoid creating dust, wash their hands after touching it, and keep it away from food. Science does not make the stone more frightening. It makes the stone clearer. We know why it is beautiful, why it is useful, and why it requires care. There is a very particular calmness in thinking about this. Inside a Galena crystal, the atoms do not run around in chaos. They sit in an order. That order creates shape. That shape leads to cleavage. The lead content creates weight. The surface creates metallic luster. The electrical properties create the ability to rectify signals under suitable conditions. And all of these things can be understood through observation, experiment, and theory. Galena therefore does not need to be made mystical. Its scientific truth is already deep enough to surprise us quietly. If we return to the image of the crystal radio, we can see it as a gentle symbol for the entire story of Galena. A piece of ore born from the darkness of rock, a thin metal wire touching the gray surface, an invisible signal traveling through the air, a small sound appearing in an earphone. There, the underground world meets the sky. A mineral meets electromagnetic waves. Natural history meets technological history. And humans, through patient curiosity, learn how to let an object that seemed silent take part in the conversation of the world. But before Galena ever helped people listen to radio, and before humans clearly understood semiconductors, it was known in a much more practical way. Ancient people realized that this ore could produce lead, a soft, heavy metal that melts easily and can be shaped easily. Lead entered pipes, roofs, printed type, alloys, bullets, batteries, radiation shielding materials, and many other industrial stories. From the atomic order inside the crystal, the journey of Galena will now expand into human history, where a useful metal also slowly revealed the cost that science had to learn how to name. From a small piece of Galena in a crystal radio, the story begins to expand beyond that quiet room, reaching back toward ancient furnaces, dark mines, rooftops, pipes, printed letters on paper, heavy batteries, and even radiation shields in hospitals. Because before Galena was seen as a natural semiconductor, humans knew it in a much more practical way. This was a mineral that could produce lead. And lead, with all its softness, weight, low melting point, and easy shaping, entered human history very early. Galena is the most important lead ore in nature. This does not mean every Galena specimen has the same mining value, because an ore body must have enough reserves, enough grade, and the right economic and technical conditions. But in terms of mineralogy and economic geology, when humans look for sources of lead in the Earth's crust, Galena is always the central name. It contains lead in the form of lead sulfide, and when it is mined, crushed, processed, and smelted properly, it can become a source of metallic lead for many different purposes. One reason humans discovered lead early is that it has a relatively low melting point compared with many other metals. Lead melts at about 621 degrees Fahrenheit, or about 327 degrees Celsius, much lower than iron. This made lead easier to melt in ancient furnaces than metals that required higher temperatures. With early metallurgical techniques, an ore that could produce a soft, heavy, easily cast metal was a major advantage. So Galena was not only a mineral in rock, it was an early doorway that led humans into the world of heavy metals. When lead is separated from ore, it has a silvery gray or pale bluish-gray color when freshly cut, but its surface can gradually tarnish when exposed to air. It is soft, easy to flatten, easy to bend, easy to cast into molds, and relatively resistant to corrosion under many conditions. Those properties once made lead useful in water pipes, roofs, soldering materials, alloys, decorations, construction materials, coatings, bullets, printing type, ceramic glazes, and many other objects. Not because lead is a perfect metal, but because it is easy to work with, easy to deform, and useful for the technical needs of different periods. But even inside that story of usefulness, we need to keep a careful tone. When we say lead was once used in water pipes, ceramic glazes, or paint, we do not mean those uses are considered safe according to modern knowledge. History is not always a history of choices that were correct from the beginning. Many uses of lead appeared before humans fully understood its toxicity. Later, medical science and toxicology showed that lead can seriously harm the body, especially the nervous system and the development of children. Because of this, many older uses of lead have been restricted or removed from modern life. This is what makes galena such a clearly two-sided mineral. On one side, it supplied lead for technologies that were once very important. On the other side, it forced humans to learn that a resource cannot be judged only by the question, can we use it? We also have to ask, where is it used? Who is exposed to it? How does it spread into the environment? How can it be recycled? And is there a safer replacement? In this way, galena tells not only the story of extraction, but also the story of applied science growing up. Another important detail is that galena is sometimes connected with silver. In some deposits, galena can contain silver as a very small impurity, or it can occur with other silver minerals in the same ore system. Because of this, many lead mines in history were also valuable because of silver. But we need to be precise. Galena does not simply turn into silver, and not every galena specimen is rich in silver. Silver can be present at different levels depending on the deposit, the stage of mineralization, and the geological conditions. The presence of silver in some ore systems is what made certain galena deposits especially attractive to humans. Imagine an old mine in a cold mountain region. Rock is brought up from underground, not as glittering gemstones, but as heavy gray ore mixed with sphalerite, pyrite, quartz, or calcite. The miner sees not only rock, but the possibility of lead, and sometimes silver. The ore is broken, crushed, processed, and then sent into a furnace. Heat changes the nature of matter. Smoke, slag, molten metal, the sound of tools, and the glow of fire create a scene very different from the silence of crystals inside rock. Galena, born slowly in darkness, steps into history through fire and labor. During the smelting of lead sulfide ore, sulfur has to be handled, and lead has to be separated from its original compound. Modern metallurgical processes are far more complex than the image of a simple fire furnace. They may include roasting, oxidation, reduction, refining, and control of emissions. What matters for our story is not going too deeply into metallurgical technique, but understanding that taking lead from galena is not simply melting rock. It is a controlled chain of chemical transformations. If that chain is carried out unsafely, lead dust, fumes, and waste can become health and environmental problems. Lead entered architecture in very specific ways. Because it is soft, durable, and relatively resistant to corrosion, lead was once used in roofs, gutters, linings, and certain construction details. In old buildings, lead may be present in stained glass windows, in the strips that hold the glass, or in protective waterproofing parts. Here, lead does not tell a story of bright beauty, but a story of a material working quietly. It is not always in the most visible place, but it appears where weight, softness, sealing ability, and durability are needed. Lead also once played a role in printing. For many centuries, lead-containing alloys were used to cast type in traditional printing. A small piece of type, cast from a soft and easily shaped alloy, could print thousands of impressions on paper. Seen this way, galena is indirectly connected to the history of spreading knowledge. From lead ore underground, through metallurgy, through printing type alloys, part of this matter took part in the journey of books and newspapers. But even here, we should not romanticize it too much. Hot metal printing also carried occupational risks, and modern understanding helped humans move towards safer technologies. In the field of energy, lead still has an important role through lead-acid batteries. This type of battery has been widely used in vehicles, backup power systems, and many applications that need electricity storage. Lead-acid batteries have the advantages of mature technology, relatively low cost, the ability to provide strong current, and especially well-developed recycling systems in many places. But once again, the word recycling is truly good only when it is carried out within a safely controlled system. Improper lead recycling can cause serious pollution, especially when dust, fumes, or lead-containing waste escape into the environment. Lead is also used as a radiation shielding material in some medical, industrial, and research settings. The reason lies in lead's high density and large atomic number, which help it absorb or reduce some ionizing radiation effectively in suitable designs. Lead aprons used in X-ray imaging, shielding walls in equipment rooms, or protective layers in certain radioactive systems all depend on that very physical property. But lead here is not a casual material. It must be used according to safety standards, with the correct thickness, in the correct position, under the correct procedures, and without becoming a source of chemical exposure. Looking back, we can see that Galena has connected the underground world to many places that seem unrelated. An ore mine can lead to a smelting furnace. A furnace leads to metallic lead. Lead enters roofs, batteries, devices, shielding materials, printing, ammunition, coatings, and many industries. But that flow is not only a flow of matter, it is also a flow of understanding. At first, humans knew lead because it was easy to use. Later, humans knew lead because it was dangerous when exposure happened in the wrong way. And then humans had to learn to use less of it in unsuitable places, replace it with other materials when possible, control it carefully when it is still needed, and recycle it responsibly when products reach the end of their lives. There is a very clear lesson in the history of leaded gasoline. In the last century, lead compounds were once added to gasoline to improve engine performance. For a time, this was seen as a useful technical solution. But later, scientific evidence about lead toxicity and air pollution led to the gradual removal of leaded gasoline in many places around the world. That story is not only about Galena, but it is part of the history of lead. And because Galena is the most important lead ore, it helps us understand the central message more deeply. A material can once be praised for its usefulness and later be reconsidered through health and environmental science. Lead-based paint is a similar example. In the past, some lead compounds were used in paint because they provided color, durability, or certain technical properties. But when old paint peels, lead-containing dust can become a source of exposure, especially dangerous inside living spaces. Because of this, many countries have strongly restricted or banned the use of lead in household paint. This shows that progress is not only about inventing new materials, but also about knowing when to stop using a material in places where it causes harm. From a distance in this story, Galena reminds us that every natural resource has a social life after it leaves the rock. Perhaps that is why, when telling the story of Galena and human history, we should not use a tone of simple victory. Just because humans can mine ore does not mean humans have defeated nature. Just because humans can melt metal does not mean knowledge is complete. The real victory comes later, when humans learn to measure lead levels in blood, recognize contamination in soil and dust, design factories with filtration systems, restore waste sites, recycle batteries in closed loops, and say no to applications that are no longer safe. That is a quiet form of civilization growing up. In old mining towns, that story often becomes clearer than almost anywhere else. Some places carry the trace of Galena in their names or in their history of lead mining. But every specific place should be checked through local records before being discussed in detail. What we can say with more confidence is this. In many lead mining regions, human communities formed around ore. Roads, houses, factories, trade, and working life revolved around ore bodies hidden inside rock. A dark gray mineral from underground could influence the economic map and the memory of an entire region. But the memory of mining is not only the light of work and development. It also includes dust, wastewater, tailings, workplace accidents, occupational exposure, and lands that need long-term monitoring. Saying this is not meant to make the story heavier than necessary, but to keep the science honest. Galena has the beauty of crystal form and the value of ore. But once it enters an industrial chain, it must be managed as a source of lead. And lead is an element that must be treated with serious caution. One noteworthy point is that lead is highly recyclable, especially in the lead-acid battery industry when the system is well organized. When an old battery is collected properly, lead can be recycled to make new batteries or other products, reducing the need to mine new ore. This is a positive side of resource management, but it does not happen automatically. It requires laws, technology, monitoring, protected workers, acid handling procedures, and control of dust and emissions. Unsafe recycling can turn a solution into a new source of pollution. So with lead, the word life cycle is very important. From ore to product to use to collection to recycling or final disposal. If we return to the Galena specimen on the table, we can see that entire history compressed inside a very quiet object. Its lead-gray surface does not speak with a voice, but it suggests many questions. Who mined it? Which mine did it come from? Did it carry silver with it? Was it ever crushed in an ore processing plant? If it were smelted, where would its lead go? Into a car battery? Into a radiation shield? Into an industrial product? Or would it rest quietly in a specimen box, used to teach a young person about mineralogy and responsibility toward matter? That question makes Galena a true historical character. It does not only have a geological past, it also has a human past. In geology, it is the result of hot fluids and chemical reactions. In civilization, it is the source of a metal that is both useful and dangerous. In materials science, it once helped rectify radio signals. In environmental medicine, it reminds us of lead toxicity. In resource economics, it raises the issues of mining and recycling. Very few minerals can connect so many layers of story while still keeping such a simple outward appearance. And right here we can understand why Galena should not be described as a mystical stone. It does not need mystery. The truth is already deep enough. An ore body can be born in carbonate rock, pass through a furnace, become lead, take part in industry, help store electricity in batteries, shield radiation in medical equipment, and still force humans to remove lead paint, phase out leaded gasoline, and control lead dust. That is not a story of magic. It is a story of matter, knowledge, and responsibility. From Galena, humans learned something very slow but very important. A resource is not valuable only because it can become a product. A resource is also valuable because it forces us to understand the consequences of that product. When we take lead out of rock, we are not only taking a metal, we are opening a chain of decisions. How should it be mined? How should it be smelted? Where should it be used? How should workers be protected? How should pollution be prevented? How should old products be recovered? And when should lead be replaced with another material? Galena is therefore a lesson in the maturity of technology. We can close this historical section with a quiet image. An old silver-lead mine after many years of being shut down. The little rails have gone silent. The furnace no longer glows red. On a table in a local museum, a Galena specimen rests inside a glass case, beside a label showing the mineral name and where it was found. Visitors passing by may see only a gray stone. But if we have followed it from underground to radio, from furnace to battery, from silver to lead toxicity, we will see that specimen differently. It is not only part of a mine, it is part of the way humans learned from the very materials they once used. And after seeing Galena in the history of mining, metallurgy, and industry, we need to step into the most important side of caution. Behind metallic lead lies one of the clearest environmental health lessons of modern science. Galena itself, resting quietly in rock, is not always a direct danger. But when ore is crushed, when lead-containing dust spreads, when lead enters paint, water, air, soil, homes, or bodies, the story becomes very different. To understand Galena properly, we cannot only say what it has helped humans do. We also have to say how humans learned to protect themselves from lead. When the story of Galena steps out of the smelting furnace and enters human life, we cannot keep only the useful sides of lead and ignore the side that requires caution. This is the part where the narration needs to slow down a little, not to create fear, but to look directly at an important scientific truth. Lead is a toxic element to the human body. It has no necessary biological role like iron in blood or calcium in bones. When lead enters the body through dust, food, drinking water, air, or occupational exposure, it can interfere with many delicate processes of life. What makes lead concerning is that it does not need to appear in a dramatic scene to become a problem. Sometimes the risk comes from something very small: a layer of dust in an old house, a flake of peeling paint, a bit of contaminated soil around an old industrial area, smoke from unsafe recycling, or ore dust in a workplace without proper protection. Lead can enter the body through breathing when lead-containing dust or fumes are present in the air. It can also enter through swallowing, especially when dusty hands touch the mouth, food, or everyday objects. For the nervous system, lead is a harmful substance that has been studied extensively. In young children, the body and brain are still developing, so lead exposure can cause more serious consequences. Major health agencies around the world emphasize that no level of lead in the blood is considered completely safe. Even low levels can be linked to reduced learning ability, behavioral difficulties, and effects on intellectual development. In adults, lead can be linked to high blood pressure, kidney damage, nerve disorders, reproductive effects, muscle and joint pain, or problems with memory and concentration. These effects do not always appear immediately, so prevention remains the most important approach. But here, we need to be very precise, so we do not turn Galena into something frightening in a superstitious way. A solid Galena specimen resting inside a display box is not the same as lead dust floating in the air, and it is not the same as a more soluble lead compound entering drinking water. Galena is lead sulfide, and under many ordinary conditions, it is relatively less soluble than some other lead compounds. However, less soluble does not mean absolutely harmless. If Galena is crushed into powder, ground, dry cut, struck in a way that creates dust, or placed in an environment where people may swallow small particles, the risk increases clearly. So the right attitude toward Galena is calm but careful. A mineral collector can keep Galena safely if they understand this. The specimen should be placed in its own container, preferably a clear box with a lid, so it can be observed while reducing the risk of impact and dust. It should have a label clearly showing the mineral name and its lead-bearing composition, not to create a sense of danger, but so that other people do not mistake it for an ordinary decorative stone. After touching the specimen, you should wash your hands with soap. Galena should not be placed on a dining table, near food preparation areas, in a child's room, in an aquarium, in a pot with edible plants, or anywhere pets might lick or chew it. These principles are very simple, but they show the true spirit of science. Understand matter, then live with it responsibly. What should not be done is crushing galena at home, using it as decorative powder, using it in cosmetics, putting it into drinking water, or wearing it close to the body as regular jewelry. Some people may be attracted to its metallic gray appearance and want to turn it into a pendant. But because galena is soft, brittle, easy to chip, and contains lead, it is not an appropriate choice, especially if the item could touch the mouth, remain in long-term contact with damp skin, or end up in the hands of young children. The beauty of galena should be appreciated as a properly stored mineral specimen, not as an everyday object worn on the body. Dust is the key word in this story. A large piece of galena inside a glass case is much less concerning than fine galena powder falling on a table, sticking to hands, or spreading through the air. The chemical composition may be the same, but different physical forms can create different levels of risk. A solid stone has a harder time entering the body. A tiny dust particle can do so much more easily. That is why, in mines, ore processing plants, smelting facilities, and battery recycling sites, controlling dust and fumes is a very important part of workplace safety. People who work with lead ore or lead products need much more serious protection than someone who only observes a specimen in a cabinet. They may have long-term exposure to dust, fumes, dirty surfaces, lead-contaminated work clothes, or air inside production areas. That is why places such as lead mines, smelting plants, battery recycling workshops, old house renovation sites with lead paint, or areas that handle lead-containing materials all need safety procedures. These may include ventilation, filtration equipment, specialized respirators or masks, protective clothing, washing areas, occupational health checks, and rules to prevent lead dust from being carried home from the workplace. Science here is not found in vague warnings, but in every practical detail of prevention. In the environment, galena also needs to be viewed with a systems perspective. When ore lies deep inside rock, it is part of geology. When humans dig it up, crush it, process it, wash it, and pile up the waste material, the exposed surface area of the mineral increases greatly. Rainwater, oxygen, and chemical reactions can interact with mine waste piles. In some environments with many sulfide minerals, such as pyrite, sulfide oxidation can create acid mine drainage, making water more acidic and making it easier for metals to dissolve. The severity depends on the mineral type, surrounding rock, climate, mine design, and management practices. So when talking about acid mine drainage, we need to be careful about each specific site, but we cannot dismiss the possibility. Water flowing through an old mine area or an unmanaged waste pile can carry metals into soil, streams, or sediment. A stream that looks clear is not necessarily completely safe if it flows through an area contaminated with metals. On the other hand, not every old mine causes the same impact. The geology of each place is different, the mining history is different, the scale is different, and the restoration measures are different. The work of environmental science is to measure, collect water samples, soil samples, and sediment samples, analyze metal concentrations, track pathways of movement, and assess risk based on data, not on feelings. This brings us to a very important lesson. A mineral does not become an environmental problem simply because it exists. Problems often appear when that existence is brought into a chain of human activities without good control. Mining without proper planning, crushing ore without containment, smelting without air filtration, unstable waste piles, informal battery recycling, or using lead in products that are easy to contact can all turn a resource into a source of exposure. Galena, as a lead ore, reminds us that responsibility begins the moment we decide to take matter out of the earth. Lead recycling is a very clear example of two sides of the same action. In a well-controlled modern system, recycling lead-acid batteries can recover large amounts of lead, reduce the need to mine new ore, and keep the metal within a managed cycle of use. But if recycling takes place under crude conditions, without protective equipment, without control of fumes, dust, and waste, it can cause serious lead exposure for workers and nearby communities. Both are called recycling, but one side is responsible resource management, while the other transfers risk from old products into human bodies and the environment. In daily life, common sources of lead exposure do not necessarily come from someone holding a Galena specimen. They often come from old lead-based paint, dust in older homes, contaminated soil, lead-containing pipes or plumbing parts, certain occupations, and certain hobbies related to ammunition, ceramic glazes, soldering, recycling, or imported objects that do not meet safety standards. This is very important for viewers to understand correctly. Galena is a doorway into the story of lead. But lead risk in modern life appears in many different forms. Knowing this helps us avoid being wrongly afraid of a rock specimen, while also not underestimating real sources of exposure. With Galena in a collection, the best approach is respect. We do not need to throw away a scientific specimen just because it contains lead. We also should not treat it like a completely harmless decorative stone. A sturdy container, a clear label, clean hands after touching. No dust creation, no placement near food, no handling by young children, no grinding or drilling in living spaces. These are simple enough principles to keep the knowledge while reducing unnecessary risk. This way of handling it is similar to how a good laboratory works with materials, not panicked and not careless. We can picture a mineral collector in the evening. On the table is a small acrylic box, and inside it is a Galena specimen with metallic gray cubic faces. The collector opens the box for a moment to observe it under a lamp, without bringing the specimen close to the face, without tapping it, without scraping it, and without randomly testing it with a knife. After looking at it, they put the specimen back, close the lid, lightly clean the area if needed, and wash their hands. The scene is not dramatic, but it is beautiful in the way science can be beautiful. A stone can be loved without being made mystical. A lead-containing object can be studied without being treated carelessly. The deeper point is this: the toxicity of lead does not make Galena bad. Nature does not create minerals to serve human ideas of good and evil. Galena is simply lead sulfide, crystallized under its geological conditions. Humans are the ones who decide how to mine it, how to use it, how to control it, and how to tell its story. Without understanding, Galena can lead to dust, fumes, pollution, and illness. With understanding, it becomes an educational specimen, a subject of research, a managed resource, and a profound lesson about the limits of technology. This is why the cautionary part does not make the video darker. It makes the video more honest. A story that only says Galena is beautiful, heavy, and useful would be incomplete. A story that only says lead is toxic while ignoring geology, structure, and technological history would also be unfair. Galena asks us to hold two ideas at the same time. It is a mineral with a dark, quiet beauty and a neat crystal structure. It is also the source of an element that needs careful control. These two truths do not cancel each other out. They make the subject deeper. When we understand lead toxicity, we also understand why modern science has changed so many material choices. Lead-free paint, unleaded gasoline, stricter drinking water standards, labor regulations in lead-related industries, mine restoration, battery recycling controls, and public education are all results of a long learning process. These changes did not happen overnight. They came from medical research, environmental measurements, epidemiological data, treatment technologies, and the ethical pressure of society. Galena stands at the beginning of the story as an ore source, but at the end of the story, we see an entire system of knowledge built to help us live more safely with matter. Perhaps this is one of the most peaceful lessons a heavy mineral can offer. Peace does not mean ignoring risk. Peace means understanding risk clearly enough that it no longer feels vague. When we know how Galena should be handled, how it should be stored, what should not be done with it, and why lead needs to be controlled, we do not need to fear the stone. We only need to respect it. And that respect is where knowledge becomes most useful, not to extract more at any cost, but to know how to use, how to avoid, how to protect the body, the home, the water, and the people who will live after us. From here, when we look again at the Galena specimen inside the glass case, it is no longer a mysterious dark mass. It is a mineral that can be explained. From lead and sulfur, from the cubic crystal lattice, from ore veins in rock, from smelting furnaces and crystal radios, from lead-acid batteries to environmental regulations, everything connects along one slow thread. And along that thread, lead toxicity is not a dark ending, but a necessary reminder that helps humans grow more mature in the way we live with resources. Once we have seen both the beauty and the safety limits of Galena, we can move into a lighter but still important layer: common misunderstandings, little-known details, and ways to recognize this gray ore among many other metallic minerals. Once we understand that Galena is both beautiful and something that should be handled carefully, we can look at it with sharper eyes. Not eyes searching for mystery, but the eyes of a slow observer. In the mineral world, many rock samples with metallic luster, dark colors, or silvery gray surfaces can confuse beginners. Galena is one of the minerals that can leave a strong impression, but it can also be misidentified easily if we only look at a photo or a small piece of rock outdoors. So the next step is not to ask whether Galena has any mystery. It is to ask, how can we recognize it correctly? The first misunderstanding is thinking that any mineral with a metallic shine, a dark gray color, and a heavy feel could be Galena. In reality, mineralogy does not work with only one sign. A specimen needs to be studied through several clues at the same time: color, luster, streak, hardness, density, cleavage, crystal form, associated minerals, and geological setting. Galena is usually lead gray to silvery gray, with a metallic luster, a lead gray streak, softness, brittleness, very high weight, and very clear cubic cleavage. When those signs appear together, identification becomes much more reliable than simply saying, "It looks like metal." One mineral often placed beside Galena in the memory of students is pyrite. Pyrite is famous as fool's gold because of its brass yellow color and strong metallic luster. But pyrite differs from Galena in many ways. Pyrite is iron sulfide, not lead sulfide. It is much harder than galena, usually with a hardness of about 6 to 6.5 on the Mohs scale, while galena is only about 2.5. Pyrite is brass yellow, while galena is lead gray. When two samples are placed side by side, galena usually feels noticeably heavier if they are the same size. Both minerals look metallic, but they tell two different chemical stories. Graphite can also confuse new observers in some cases because it has a dark gray to black color, a slightly metallic luster, and is very soft. But graphite is carbon, not a lead-bearing mineral. It is much lighter than galena, often feels slightly greasy or slippery to the touch, and easily leaves a black mark like pencil lead. If we hold two samples of the same size, the difference in weight appears almost immediately. Galena has the dense heaviness of lead sulfide. Graphite has the soft lightness of layered carbon. One is like a block of winter night made from gray metal. The other is like a quiet streak of charcoal that can write on paper. Hematite brings us to another kind of confusion. Some hematite samples have a dark metallic luster, a steel gray or black color, and look fairly close to certain ore minerals. But hematite is iron oxide, not lead sulfide. One very useful sign of hematite is its reddish-brown streak. Even if the surface of the sample looks gray or black and metallic, when it is rubbed across an unglazed porcelain plate, the powder color of hematite often appears reddish-brown, like a memory of iron. Galena leaves a lead-gray streak. Just one simple test, if done correctly and safely, can help us see that the surface can mislead us, while the streak sometimes tells the truth more clearly. Magnetite can also appear on the list of minerals that are easy to confuse with galena because it is black, metallic, or submetallic, and is an important ore mineral. But magnetite is a strongly magnetic iron oxide. A magnetite sample is usually clearly attracted to a magnet, while galena is not a typical magnetic mineral. Magnetite also does not have perfect cubic cleavage like galena. So if a dark gray sample is strongly attracted to a magnet, we should think of magnetite or a material containing magnetic iron, rather than quickly calling it galena. Once again, science reminds us not to fall in love with a hypothesis too soon. Let the signs speak first. There are other sulfide minerals that can appear close to galena in ore deposits, such as sphalerite, chalcopyrite, tetrahedrite, or certain silver minerals. Sphalerite is zinc sulfide. It can be brown, black, honey yellow, or reddish-brown, and may have a resinous to submetallic luster depending on the sample. Chalcopyrite is brass yellow, usually softer than pyrite, but still different from galena in color and composition. These minerals can occur with galena in the same ore vein, making field samples more complicated. So when we look at an ore sample, we should not assume every metallic-looking area is galena. One rock can contain many minerals at the same time, and each mineral holds its own piece of information. Another misunderstanding is thinking that every galena specimen has perfect cubic crystals, like museum photos. In reality, that is not the case. Display specimens are often beautiful samples, selected because they have sharp crystals, bright surfaces, and clear shapes. In mines or within host rock, galena can appear as massive material, tiny grains, metallic streaks, irregular patches, or areas covered by other minerals. Some freshly broken samples are bright and strongly reflective. Others have been exposed to air for a long time or lightly weathered, so they look duller. These differences do not remove galena's identity. They simply remind us that nature rarely presents specimens as perfectly as they appear inside a glass case. A freshly broken galena sample may look brighter because the broken face is still fresh, not yet tarnished or covered by a surface alteration layer. But a bright surface should not be understood as a sign of energy or anything mystical. It is a matter of mineral surface and light. When a lamp touches a flat cleavage face, the surface reflects it with a cold, bright impression. When the surface is scratched, covered with dust, lightly oxidized or coated with another mineral, that shine may become weaker. The beauty of Galena is therefore not a miracle. It is the result of structure, surface, and the way matter interacts with light. Some people are drawn to Galena's heavy feeling and attach unsupported meanings to it, such as calling it a healing stone, a body-protecting stone, or a stone with strong energy. In a scientific script, we need to say clearly and calmly, there is no reliable medical evidence that Galena heals disease when it is held, worn, placed under a pillow, or kept in a room. On the contrary, because Galena contains lead, using it as something that frequently touches the body, grinding it into powder, putting it into water, or using it in cosmetics should not be done. The true value of Galena is not found in vague healing promises, but in mineralogy, geology, the history of metallurgy, semiconductor physics, and the lesson of safety. Historically, some lead-bearing mineral substances were used in cosmetics or eye paints in certain ancient cultures. When telling this detail, we need to clearly separate historical fact from modern recommendations. The fact that something was used in the past does not mean it is safe or should be repeated today. History shows us that humans once viewed minerals through the needs and knowledge of their own time. Modern science allows us to look back at those practices through toxicology, medicine, and safety standards. So Galena may appear in the story of ancient cosmetics as a cultural trace, but it should never be presented as a modern beauty ingredient. The Old English name lead glance is also an interesting detail. The word glance suggests a sparkle or a reflected shine on the surface of lead ore. That name shows that people noticed the metallic luster of Galena very early on. But a name is only an entrance. Behind the name is an entire system of identification. Galena does not only glance or shine. It is also heavy, soft, brittle, has a lead-gray streak, has cubic cleavage, and is the main ore of lead. When we learn enough of these signs, the name gains a body, a weight, and evidence. In museums, Galena sometimes stands beside minerals that are far more colorful. Quartz can be as clear as ice. Malachite has layered green bands. Fluorite can be purple, green, or yellow. Azurite has a deep blue color. Beside them, Galena may look quiet and less inviting. But if viewers pause for longer, they will see that Galena's beauty is the beauty of geometry and weight. Its cubic faces are like a mathematics lesson written in stone. Its cold, metallic faces remind us of electrons and light. Its weight reminds us of lead. A small specimen can open more layers of knowledge than its first appearance may suggest. That fits very well with the way science teaches us to look. Science does not only search for dazzling things. Science also loves silent objects, dark objects, things that may not attract attention at first, but contain a great deal of information. Galena does not need to compete with gemstones for brightness. It has its own beauty, the beauty of a mineral that holds structure, history, lessons about technology, and lessons about toxicity. Someone who understands Galena may walk through a gallery and stop longer in front of that gray block, not because it is beautiful like jewelry, but because it is a meeting point between the underground world and civilization. Another misunderstanding is thinking that the larger and heavier a Galena specimen is, the more powerful it is in a mystical sense. In science, greater weight only tells us that the mass is greater or the volume is larger. It does not tell us that the object can heal, protect, or create any special mental effect. A large galena block may be impressive because of its high density and because it contains more lead sulfide. It may be valuable as a collectible if the crystals are beautiful, the origin is clear, or it occurs with other minerals in an attractive way. But what makes it worthy of respect is its material data and geological story, not an unverified, invisible power. In education, galena is a very good specimen if it is managed safely. It helps learners understand that minerals have chemical formulas, crystal structures, physical properties, and geological settings. With only one small sample, we can talk about Mohs hardness, density, metallic luster, streak, cleavage, metal ores, lead-zinc deposits, metallurgy, crystal radios, and lead toxicity. But precisely because it is a lead-bearing specimen, a classroom needs clear instructions. Do not put it near the mouth, do not scrape it into powder, do not drop or break it, wash hands after observing it, and store it separately. A good specimen does not only teach knowledge, it also teaches safe habits. Some galena specimens become especially beautiful when they occur with quartz, calcite, sphalerite, pyrite, or barite. Quartz can create a bright background that makes the lead gray galena blocks stand out more clearly. Calcite can create contrast through white, cream, or translucent colors. Sphalerite can add brown or glossy black tones. Pyrite sometimes adds a brass yellow shine, helping viewers see the difference between iron sulfide and lead sulfide within the same specimen. That combination is not only beautiful, but also geologically meaningful. It tells us that these minerals may have formed in the same ore system, or may have appeared through several different stages of fluid movement. Some cubic galena specimens are so beautiful that they look as if they were cast in a mold. But this itself is a chance to explain science. Crystals do not need human hands to create geometry. Under suitable conditions, atoms arrange themselves into a crystal lattice, and the outer shape can reflect the inner order. So a galena cube is a gentle lesson that geometry is not only found in math books. It appears in salt, in pyrite, in fluorite, in many other minerals, and here, in a dark lead ore. Nature doesn't draw with a ruler, but sometimes its results are surprisingly straight, square, and orderly. We should also talk about the difference between beautiful online photos and real specimens in everyday life. Studio lighting can make galena look brighter, sharper, and almost perfect. Macro photography can enlarge tiny crystal faces so much that viewers may think every sample looks that way. In reality, many galena specimens are duller, more chipped, more mixed with rock, and less stage-ready. That does not make them less real. On the contrary, it reminds us that science does not only work with the most beautiful specimens. Science works with real objects, even when those objects are messy, asymmetrical, and require careful observation. If viewers want to identify a sample they suspect may be galena, the safest approach is not to begin by damaging the sample. Observe its color, luster, relative weight, shape, broken faces, associated minerals, and where the specimen came from. If a streak test or hardness test is needed, it should be done very gently, under controlled conditions, while avoiding dust and washing hands afterward. With a sample of unknown origin, or one suspected to contain lead, the best choice is to ask a professional, a laboratory, a geology museum, or a responsible mineralogy community. Knowing our own limits is also part of scientific observation. The misunderstandings around galena eventually bring us back to the same point. Its true value does not need to be exaggerated. It is already special enough because it is lead sulfide. It is already memorable enough because it feels heavier than it looks. It is already beautiful enough because it has cubic cleavage and a lead gray metallic luster. It is already deep enough because it forms from fluids underground. It is already important enough because it is connected to lead, silver, metallurgy, crystal radios, industry, and environmental toxicity. When an object has so many layers of truth, we do not need to add unverified promises. Accuracy makes it brighter, not poorer. Perhaps a museum scene is the gentlest way to close this layer of understanding. Imagine a quiet glass case where Galena rests beside quartz, calcite, and sphalerite. A person walking by at first sees only a gray stone. But after learning its weight, its formula, its cleavage, its history, and the caution required with lead, that person pauses longer. They do not see Galena as a protective charm, and they do not see it as a terrifying poison. They see it as a real mineral with real beauty, real risk, real history, and a real ability to teach humans to look at matter with clearer awareness. And after all that identification, comparison, misunderstanding, and correction, Galena still leaves behind a deeper meaning. It reminds us that humans usually encounter matter in stages. At first, there is curiosity about appearance. Then comes extraction for usefulness. Then comes understanding of structure and mechanism. Finally comes responsibility toward health, the environment, and the future. A dark gray lead ore resting quietly inside a glass case can contain that entire journey of growth. And from here, the story of Galena can move toward its final layer of reflection. The weight of a stone sometimes does not rest only in our hands, but also in the way we learn to live with knowledge. And after a piece of Galena has passed through all those layers of understanding, from the lead gray color on its surface to the crystal lattice inside, from ore veins underground to smelting furnaces, crystal radios, lead-acid batteries, and then the lesson of lead toxicity, we begin to recognize something very slowly. The weight of Galena does not only rest in the hand, it also rests in the way this stone forces humans to think more deeply about matter, technology, and responsibility. At first, Galena makes an impression through a very direct feeling. A small specimen, but heavy. A metallic gray surface, but not dazzling. A crystal that can break along square, flat faces, as if there is a quiet order inside it. That is physical weight. The weight that comes from the element lead inside the lead sulfide structure. But if we stop there, we have only understood Galena with our hands. When we continue listening to its story, we begin to understand it with the mind, with history, and with the caution of science. A small piece of Galena may have been born from hot fluids moving through fractures in rock. It may have grown in darkness, without sound, without light, without any human witness. Then, across geological time, the rock was lifted, eroded, cut open by mining, or picked up as a mineral specimen. At that moment, something that once rested quietly underground entered human life. It was no longer only a chemical precipitate. It became ore, geological data, a resource, and an ethical question. In mineralogy, Galena teaches us that appearance is only the beginning. A gray color is not enough for identification. A metallic shine is not enough for a conclusion. A heavy feeling is not enough for understanding. We need chemical composition, cleavage, streak, hardness, density, geological setting, and associated minerals. That way of looking is also the way science looks at the wider world. Science does not rush to trust the first impression. It gathers many signs, tests each possibility, removes misunderstandings, and only then reaches a conclusion. Galena, through the very fact that it is easy to confuse with other minerals, teaches us the patience of observation. In the history of technology, Galena teaches another lesson. A dark piece of ore once took part in early crystal radios, where humans could hear distant voices through a simple electrical circuit. A mineral born in the darkness of rock became part of a device that captured invisible signals in the air. That image is beautiful, but it is beautiful because there is a real scientific mechanism behind it. No magic, no mystical energy, only electromagnetic waves, a signal-selecting circuit, contact between a metal wire and a crystal, and the natural semiconducting property of lead sulfide under suitable conditions. That truth is subtle enough to surprise us without adding anything unverified. In industry, Galena shows how humans learned to use resources to build many layers of civilization. Lead from ore-entered construction materials, alloys, printing type, batteries, radiation shielding devices, and many other applications. But that history is not a straight line made only of success. It also includes mistakes, exposures, and products that were once widely used and later had to be restricted because of toxicity. Here, Galena becomes a very clear lesson. A material can be useful in one setting, but dangerous in another. The question of science is not only, can it be used, but also, how can it be used without harming people and the environment? No mineral carries morality in the human sense. Galena is not good, and it is not evil. It does not intend to heal, and it does not intend to harm. It is simply lead sulfide crystallized under suitable geological conditions. Morality appears when humans decide to mine it, crush it, smelt it, sell it, place it in a home, use its lead in products, or allow its waste to come into contact with soil and water. So the ethical weight of Galena does not lie inside the crystal itself. It lies in the chain of human actions surrounding that crystal. This is what makes Galena a very modern mineral, even though its history is ancient. It forces us to see resources as a system. We cannot look only at the ore deposit and forget the workers. We cannot look only at the product and forget the waste. We cannot look only at lead-acid batteries and forget recycling. We cannot look only at a radiation shield and forget safety standards. We cannot look only at a beautiful specimen inside a glass case and forget that it contains lead and needs proper storage. To truly look at Galena means to look at the entire path of matter, from the underground world to the hand, from the factory to the river, from technology to the human body. Perhaps human maturity in front of Galena can be told in 3 very slow steps. First comes, we can use it. Ancient people saw that the ore could produce lead, that lead melted easily, cast easily, and shaped easily, so it became an important material. Then comes, we can understand it. Science gradually came to understand the lead sulfide composition, the crystal structure, the hydrothermal origin, the semiconducting properties, the toxicity of lead, the pathways of exposure, and the environmental impacts. Finally comes, we can use it more safely. Humans created regulations, replaced lead in many applications, controlled factories, restored mines, recycled under managed systems, and provided guidance for storing specimens. Real progress lies in this 3rd step. If humans only extract more, they may become rich in materials but poor in understanding. If humans only fear and avoid, they may miss a valuable scientific lesson. But if we understand Galena from both sides, we can keep a balance. We can admire a lead-gray cubic crystal and see its beauty. We can tell the story of crystal radios and find it fascinating. We can acknowledge the role of lead in industry and see its importance. At the same time, we still know that lead needs to be controlled. Lead dust needs to be avoided. Children need to be protected. Old mines need to be monitored. And recycling needs to happen inside a safe system. That is the beauty of mature knowledge. It does not oversimplify the world, but it helps us live with the world more wisely. A piece of galena in a museum can therefore become a very quiet lesson. It does not move. It does not speak. It does not change color to draw attention. But if we know how to listen through understanding, it tells of hot water underground, carbonate rock, sulfur, lead, silver in some deposits, smelting furnaces, letters once cast from lead-containing alloys, batteries, radiation, old paint, dust, flowing water, the hands of workers, and the caution of mineral collectors. All of that is held inside a specimen with such a simple appearance that many people might walk past without stopping. There is something very beautiful in the way our vision changes. At first, a viewer may see galena only as a dark, heavy stone. After this journey, the stone has not changed, but the way we see it has changed. We do not make galena brighter with a lamp. We make it brighter with knowledge. We do not make it lighter with our hands. We make its weight more meaningful through understanding. This is one of the quietest gifts of science. It does not always make the world simpler, but it makes the world less vague. And when vagueness fades, the human mind can become calmer. That calmness is very important. In many stories about toxic materials, people easily fall into two extremes, either dismissing the risk or panicking over it. Galena does not need either extreme. It needs accuracy. A galena specimen in a box, stored properly, is not a reason for fear. But powdered galena, lead dust, unsafe smelting, uncontrolled battery recycling, peeling lead paint, or lead-contaminated water are real problems. When we can distinguish these things, we do not only understand galena, we learn how to separate real risk from vague fear. That is a very valuable scientific skill in everyday life. Galena also reminds us that natural resources always have a past before they belong to humans. Before it becomes ore on a mining map, it is a reaction inside rock. Before it becomes lead in a battery, it is a crystal in a mineral vein. Before it becomes a specimen on a shelf, it is part of a larger geological system. When we understand this, we become more humble. Humans did not create galena from the beginning. Humans only found it, named it, mined it, studied it, used it, and became responsible for the part they took from underground. That humility does not weaken science, it makes science deeper. A lead ore underground can connect to many places on the surface. It can be connected to an old mine on a mountainside, a quiet geology museum, a crystal radio in the history of communication, a battery in a vehicle, a backup power system, an X-ray room, a regulation about lead-free paint, a drinking water testing program, a piece of land that needs restoration, and even the hands of a collector washing them after observing a specimen. That path shows that mineralogy is not a subject only about rocks. It is connected to economics, medicine, the environment, technology, history, and the way humans live with the planet. That is why galena is a mineral well suited for ending with reflection, not with a loud conclusion. It is not the brightest stone. It is not the hardest mineral. It is not the safest material to touch carelessly. But it is one of the minerals that can teach us a great deal through its silence. It teaches that beauty can lie in structure. Value can come with risk. The history of technology can begin with simple raw materials, and environmental responsibility often begins with correctly understanding the nature of what we are using. If we return to the first image, a block of galena resting in the palm of the hand, we can feel that original moment again in a new way. At first, its heaviness was only surprising. Now that heaviness has many more layers. It is heavy because of lead, heavy because it was formed across geological time, heavy because it once entered smelting furnaces and industry, heavy because it is connected to silver, radio, batteries, and radiation shielding. Heavy because it reminds us of lead toxicity and environmental lessons. And heavy because it helps us understand that knowledge is not only for taking more from nature, but also for knowing when to stop, when to replace, when to protect, and when to listen. At the end of the main section, galena no longer appears as a simple gray stone. It becomes a connection. One end of that connection lies in the darkness underground, where hot water, lead, sulfur, and rock create crystals. The other end lies in the human world, where mining, technology, health, and the environment intertwine. Between those two ends is science, not loud but persistent, helping us read matter through evidence instead of imagination. And perhaps that is the quietest gift galena offers. It does not only tell us where lead comes from, but also reminds us that everything humans take from the earth should be understood with both intelligence and care. And so, from a lead gray ore resting quietly inside rock, galena has opened a journey far longer than its appearance might suggest. We have learned that galena is a lead sulfide mineral with the chemical formula PbS, and that it is the most important natural ore of lead. We have understood why it feels heavier than its small size, why it has a cold metallic luster, why it is soft and brittle, and why it can split along neat cubic faces like a geometry lesson written underground. We have also followed galena deeper to the place where hot fluids quietly move through fractures, carrying lead, sulfur, and the necessary chemical conditions to create crystals. Then, from that underground world, galena stepped into human history, into smelting furnaces, into the story of lead and silver, into the earliest crystal radios, into lead-acid batteries, into radiation shielding materials, into industry, and also into very serious lessons about lead toxicity. Perhaps the most memorable thing is that galena does not need to be made mystical. Its true nature is already deep enough, strange enough, and beautiful enough. It is a heavy block of winter night from the underground world, where science can read the history of matter, technology, environmental health, and human maturity in the way we use resources. Galena reminds us that knowledge does not only help us extract from nature, it also helps us understand limits, protect the body, protect flowing water, protect the land, and protect the people who will live after us. Now, imagine that piece of galena being placed back into its specimen box. The laboratory light slowly softens across its lead-gray surface. It remains as silent as it was at the beginning, but in our minds, it is no longer a nameless stone. Thank you for listening to this gentle science journey with Sleepy Drift into Knowing. I wish you a truly peaceful night, a soft and restful sleep, and I will see you again in the next exploration.